All right, welcome back. I hope you're having an amazing time so far. Our next speaker is Jin Zhao. She is a senior machine learning scientist at Amazon. Please join me in welcoming her to our virtual stage.
Hi, everyone. I'm Jin. I'm a scientist at Amazon, and today the topic is the interdisciplinary nature of human learning and the techniques for understanding and improving how humans learn. As we all know, human learning and improving human learning is a huge topic. We started learning as a baby, and we're experiencing it every day and hour. However, we don't think much and learn much about it. And the truth is, we're not yet able to come up with a comprehensive understanding of what human learning is, what we can do to improve the process of learning. Humans have been trying hard to understand what learning is, but it is not easy. And here is the 4 reasons why it is not easy, in my opinion. First is it is covert nature of human learning. There's no access to the ground truth of it, ground truth of how we learn in the most effective way for each of us. We learn by doing, by failing, by reflecting, and sometimes we learn through observations of ourselves and others. But we have no direct access to the covert mental process, the brain. The second is learning is different for each individual since everyone has a personalized mode of learning and a very unique way to perceive and justify the world. The third is the education system has treated us all the same in giving us the knowledge that they think we should develop when we were kids. They didn't consider what I need and how and when I want to learn it. Sometimes the way we got trained adds more difficulty to learn new things because we have to unlearn things first. And the fourth is the metacognitive skills were not fully built yet, but should have been developed as we were a kid. The metacognitive skill is the skill of learning how to learn how I should learn. Studies have shown kids who have developed such skills when they were 4 to 8 years old, they could outperform in their studies 10, 15 years later. But there's little teaching in school on metacognitive skills and even no teaching on how important it is. So these 4 aspects make the human learning pretty interesting, and we are making an attempt to discuss it today. I'll be talking about the research work I've been doing in the past 2 years at Amazon on human learning, and also the applications that are implemented in that corporate setting. So I will decouple the two topic into several subtopics and share some findings around how to use machine learning / data science, cognitive science, learning science to help understand what it is and how we could improve it. All right, let's step back and think about what is learning. Reading in a library, going through assignments, discuss with groups in a classroom, or learning through online, or even through all kinds of experiences you come across, like this event. Today, we'll be focusing on only the online learning through which the adaptive, personalized learning experiences can be delivered to individuals and at scale. So what is online learning? Select platform, Coursera, MOOCs, online classrooms from universities, pick a course you're interested. Let it be NLP, computer vision, deep learning, 231, and to follow whatever is presented to you, read content, answer those thematic questions, quiz, session after session, you take the final assignment before you get some form of certificate. So here's my question. How comfortable are you in such learning experiences? Do you like, how much you like, or anything you think could be improved for you? We would probably wonder, what does the certificate mean? What does the degree mean? And how much knowledge I've learned from these learning experiences that I can apply directly in my projects? And what is the gap for me to deliver an end-to-end project after learning all these? Should I spend time on those assignments? Is it helping me to deliver that end-to-end project? If not, what are the alternatives that is worth my energy and attention? In short, as a human, we always wanted to be validated, but only validated in the right approach that is helping achieve our goals. Are those assignments the ones through which my skills can be validated for my projects? We not only want it to be validated, we also want it to be understood in general and also in this learning context. We want it to be understood by the tutorial system, by the algorithms behind the screen. Is that feedback for me, not for everyone, because I'm different? Today, we'll be discussing the state-of-the-art models, frameworks, techniques that can help us deliver a more effective and efficient learning experience to learners, an experience that understands what the learner needs, and it provides good practice opportunities so that a learner can not only develop the desired skill, but also gradually develop the metacognitive skills. We have focused on learners only, but in the ecosystem, we have other players like learning designers and learning scientists, practitioners. So let's also think about what is in each player's interest. As a learner, I wanted to know where I am, what is the path forward to things yet to learn, and how I can demonstrate the skills I have developed and to feel good about myself. As a designer who creates learning experiences, I want to discover what is working and what is not working for my audience, how I can improve the design for whom in developing what skills, and how to better structure the knowledge so that I can observe easily where learner got stuck and how I can provide feedback to help them out. As a research scientist, I want to discover what insights are helping learners to understand where they are, how to proceed, and what insights are helping designers to understand how effective the experiences are, where to improve and how. And the findings that augment learning science theories and practices to find the truth of learning. So here's the subtopics I want to introduce to you to get you into the story, and hoping that you will start thinking about learning every time you learn. So the first topic is student model of learning. What is it? A student model is a model that estimates where the student is in learning something. Where refers to the knowledge state. For instance, 100% mastered or 60% proficient on a subject. Why we need knowledge state estimation? Knowing where we are is the first step in deciding how to proceed. And having such access to where we are at each step, we can gradually develop the sense of how we learn, which is the metacognitive skill. However, knowledge tracing is not easy because learning is covert. But there should be ways to observe how the brain is functioning, right? And there are different ways to observe that. Brain imaging is for sure a solution, and attaching sensors to a body to collect the biological signals, in addition to brain imaging, is another. There are cutting-edge research around those notions, but for today, we'll be only talking about using quiz, formative assessments to estimate the knowledge state. For instance, using a multi-choice, single-choice matching quiz, even an open-ended constructive response question to understand and evaluate where you are, whether you're good to move on. So in order to ensure the system is able to make a confident and accurate estimation, usually learners will be provided with a minimum number of exercises to demonstrate that you're not guessing, not cheating. And the minimum number of exercises is decided by the complexity of that skill. And for each exercise, learners can always make as many attempts as they need to practice. And they learn from those attempts because there will be feedback provided to them as they fail on an attempt on a particular question. So after learners have practiced all these exercises, the system has collected all this sequential behavior, and some mathematical model will take that sequential input to estimate your knowledge state. That model is the knowledge tracing model. So knowledge tracing is the task to look at the sequential data and estimate where you are, but based on what? We don't have the access to a ground truth. Thus, define a proxy of the truth is the first subtask in conducting a knowledge tracing task. But sadly, there isn't much work around how to find a better proxy of the truth. After defining such truth proxy, how to make the algorithm more accurate, reliable, interpretable is the second subtask. So I've made some effort on building a student model, and here are two publications. The first one is I try to define a truth proxy as the average correctness of the successive n attempts. Let's say you failed on the current attempt, but you are able to constantly succeed in the following 5 attempts on the successive assessments, then it indicates that even you failed, you've learned something so that you're able to solve that successive problems. So your current knowledge state will be estimated, let's say 90%, close to proficient. Let's assume 5 is a sensible number of evidence you need to demonstrate the skill. People usually look at only the next attempt correctness as the truth. And I don't feel that comfortable because we need a consistent signal to be able to estimate confidently. And that is why I propose to look forward with the successive N attempts. The N needs to be defined by the course designer based on the type of skill and the complexity of the skill. So in this figure, all the rest attempts correctness is average as a proxy, just to illustrate the idea. So as a result, with a few steps forward looking, we can observe a clear trajectory of both actual and estimated knowledge state. And the accuracy of the estimation is good. The blue line is the estimate and the yellow line is the actual. The actual means the proxy we defined at the beginning. So in comparison, if we only use the next attempt correctness as the proxy, there's almost no pattern can be observed. You answered either right or wrong. It is binary, and the actual line is jumping up and down. And how can we expect an algorithm to predict accurately and confident by feeding it with randomness? That is why the blue line is the blue line of the model just give up around 6.7 accuracy and stop looking for better solutions. So few step forward looking is a need to proxy, in my opinion. But there are still questions unanswered. Should we average correctness or use some statistical models such as regression to better approximate what is happening in the brain? How to demonstrate which makes more sense? And the answer would be what makes more sense in what context? Another work I did is modeling behavior at attempt level other than at assessment level. Practically, in most of the online learning tutorial system, people aggregate attempts into assessment level and model from there. The problem with that is the details at the attempt level are sadly distinct. The attempt level information tells us how the learner is making progress. Thus, what I did is to enhance the Bayesian knowledge tracing model with the attempt level information. So the BKT is a hidden Markov model that models the probability of a learner guessing, flipping, transitioning, and the knowledge state. So we also did minimum number of exercise opportunity estimate to ensure the model produces reliable estimation. It offers insights to our designers about how many assessments they need to design so that learners will have enough opportunities to practice and demonstrate what they've learned. All right, the second topic is personalized adaptive learning. Personalized learning is not new and people have different definitions for it. I define it as a tailored learning experiences with accurate knowledge state estimation and targeted recommendations on the next learning activity. When I say accurate, I mean it is accurate to you, not accurate to an average learner. Targeted recommendation means a recommendation for you based on where you have been and where you are and what you aim for. As we just talked about the knowledge state estimation, think about what we usually do in a real life learning experience. In order to know where we are, we usually go to experienced people or mentors to help us figure out where we possibly are by describing what we want, what we did, and what we are struggling with. And since they're more experienced, they've gone through a similar learning experiences, then they might provide you an estimate on where you are and what you could probably do as the next step. And if they share some background knowledge and the same past experiences, that would be awesome because they could know you better in that way. So inspired by that thought, people who are experienced would probably know where you are. We could naturally start to think, why not let machine do the job for us? The job refers to find the people who are already experienced and look at what their learning trajectory looks like, and then look at your learning trajectory and do an estimate on where you are and what you could try based on what they've done up to that current status, the action they've taken that makes them experienced. And we could further optimize the learning trajectory by looking at the most efficient path forward for you. Yes, that is the solution. And the good thing is it not only scales, but also more practical and accurate in some cases. Because in real life, a mentor is not easy to find, connect, and the estimation from the mentor is just a perspective from someone. It might be biased, and there's no way to validate if it is biased. So what machine can do is to scan all the experiences from others, figure out what kind of people's strategy might be of help to you, and calculate your current state and next steps based on the info from others. To me, it is more transparent and much closer to the truth. And we also have some level of control with it, so why not? But we need to be prudent when we design the algorithm. What do you mean by experienced? How experienced that person needs to be, and whether the evidence is relevant and convincing. Part of the reason I love science is because every step I take will bring me closer to the truth. It also means most of the time we don't have a direct answer to those questions. And that is why we need to do experiment and discover the truth, or at least to collect some evidence to support the unknown truth, or even just prove something is wrong, something is not working. So in this application, we follow the same philosophy of doing science, and that is first we define the algorithm and then we test it out. The algorithm we came up with is to use some similarity measure to define who are similar to you and who have been proficient in that skill, and to look at what are the most common steps, next steps, and use that as a recommendation for you. And we test that in our learning platform. Sadly, I'm not able to share that right now, but I hope I can do it soon. But what I can say is I have confidence in that it works pretty well. And a sub question as we just started is how to define who are similar to you and what attributes contribute to that similarity, the similar and experienced people from which you can learn. So in order to do that, we incorporate the learner attributes to augment learner profile, and hoping machine can figure that out, figure what attributes really matter in what context. So our learner profile would include the categorical features such as tenure, job info, skill set, and also the learning patterns like the learning pace, learning style, and the machine will take everything and do its job as we ask it to do. As part of the result, which I can share, we found at the beginning of the learning experience, since we don't have enough data points for this particular learning experience, those categorical features plays a more important role in measuring the similarity. As the system collects more data about this learning experience is about you, then the learning pace, learning style contributes more in finding the similar experienced learners. So check out the paper if you're interested in this topic. So let's get into the third one, which is the targeted feedback generation and insights. One big expectation we have for tutoring system is that they can generate feedback to a learner like a coach, a teaching assistant. There are two benefits for such a feature. One is learners can receive guidance at any time when they need it. Another is it frees time for teachers to focus on other important tasks in teaching. What have been excessively looked at is how to conduct auto grading or design a one-word mapping feedback beforehand for any possible situation, so that feedback can be surfaced to the learners as needed. Auto grading is helpful, but that is not enough. We need feedback, not only a score. Tell me how I can improve, other than tell me how bad I did it, right? And for those multiple choice, single choice questions, predefined feedback is possible. For instance, if you pick this distractor, then work on this concept. But when it comes to open-ended constructive response question, it becomes difficult because the answer from a learner is no longer predefined one. And we need ability to understand what the learner answer is before we can offer any help. Thus, in this topic, we focused on generating targeted feedback for constructed response question activity. It is an NLP application. The difficulty, as I mentioned, lies in how to extract the semantics from the free-form text and match it to what is expected, and then derive the knowledge gap and provide a feedback based on this knowledge gap or the misconceptions. Especially there are more than one grading points to be measured, then things becomes even more interesting. In this example, we have 5 grading points that we're expecting from learners, and we aim to provide guidance based on what they've mastered and what they haven't out of those 5 points. So as you know, NLP application is always interesting. It is always a kind of pipeline you can build. The solution we came up with is as follows. We first segment learner answer and model answer into chunks. Then we extract the semantics from both learner answer and model answer and compare their similarity at grading point level. After that, we derive what is answered successfully and what is not. Finally, we'll provide feedback based on what is not. That is the knowledge gap the learner need more practice on. So a bit more details in both segmentation and semantic extraction. We compare graph-based, statistical-based, and semantical-based approaches to see what is working and when, and what is not working and why. Check it out. All right, I think we're quite out of time, and I will skip the next one, go to the last one, which is my favorite. It is about the skilled model of learning. So at the beginning, we've talked about the student model of learning that is about knowledge state estimation. Now we're talking about the skill model of learning. A skill model of learning or a cognitive model of learning is a computational representation of how people think about and develop that knowledge within a subject area. For instance, very broadly, as a data scientist, as you perform a data analysis, there are skills around data prep, pre-processing, build a neural net, define a metric, and studying a use case. Usually the use case study comes after you have mastered all the other steps. A skill model is expected to be fine-grained. It would be decouple the data processing into data cleaning, statistical analysis, and for statistical analysis, it will further be decoupled into different ways, skills we need to do a statistical analysis, like basic concepts like central limit theorem, maximum likelihood estimation. So a cognitive model of learning tries to structure the skills within a subject area so that designers can design a more clearly structured experience. More clearly means each step you take, you know the purpose or the desired outcome of that step. And the sequence of these learning steps fit into how usually people learn, how learn happens. So as a result, learners can learn more efficiently and naturally, learn in the flow. And at the same time, when there is something learners are struggling with, we can easily identify what it is because we know the purpose of that particular piece of design. So we can offer you help. So this is very important, but also very difficult to construct skilled model. And the difficulty comes, again, the covert nature of learning. All the best we can do is to augment human intelligence with artificial intelligence and come up with such a cognitive model of learning. It works as follows. Learning designers construct CTA, cognitive task analysis, or think aloud protocols with SMEs and unpack those knowledge into skill models. An initial model is born from human intelligence. As the course is launched and learners start engaging, we apply algorithms to discover the skill model based on the learning interaction data. So that is from artificial intelligence. A third step is to provide the discovered skill model to learners, to designers, so that designers can look at a perspective from data, revisit the course design, and incorporate the useful insights to revisions. All right, that is all. And I think there are a few other topics. I have to leave them out because of the time limit, and hope all of you started thinking about learning as you're in this session. Thank you.
Wow, thank you, Jinjin. That was amazing. I know we could listen to you talk for a long time. That was wonderful. And thank you so much for taking time to share with us today.
Yeah, they're too much. There are too much things. Wow, yeah. Just thank you so much for helping me go through this. Yeah.
Yes. So for the audience, it's time for you to make your way to your next session. Along the way, make sure you accept your connection request and take some time to check out our amazing exhibits. Thanks so much, and we'll see you around.
Thank you.